Hello everyone, this is Savannah Betkowski, Project Assistant at the Syracuse University Environmental Finance Center. On behalf of the Environmental Finance Center Network, I'd like to welcome you to our webinar entitled Ask the Experts, Energy Management and Water Supply and Distribution Systems. To give you all of an idea of where others on the webinar are tuning in from, we have prepared this map. You can see that we have attendees spread all throughout the country. Thanks to you all for joining us. Attendees can receive a certificate of attendance for viewing this webinar. This webinar has not been submitted to licensing agencies for pre-approval of continuing education credits. AWWA recommends that you check with your licensing agency to learn more about its criteria, rules, and what you need to do in order to receive credit for your attendance. It is your responsibility to verify this information with your licensing agency. If you need assistance in applying for credit to your licensing agency, please contact Education Services at awwa.org. For attendees who have an AWWA customer record, your certificate will be uploaded within 30 days of this webinar date. For attendees who do not have an AWWA customer record, you will receive an email from AWWA requesting you to create a customer record by a specific date in order to receive your certificate. If you do not create a customer record, you will not receive a certificate. This session is one of several webinars conducted by the Environmental Finance Center Network for the Smart Management for Small Water Systems project. The EFCN provides training and technical assistance to small public water systems in all 50 states and 5 territories to help local water systems achieve and maintain compliance with the Safe Drinking Water Act. And here you can see the various centers that make up the Environmental Finance Center Network. You can see that we have centers spread all across the country. And here you can see the areas of expertise that the EFCN focuses on. The EFCN also has a small systems blog that you can learn more about water finance and management through this blog. Blog posts feature lessons learned from our trainings and technical assistance, descriptions of available tools, and small systems success stories. You will also have the opportunity to subscribe to this blog at the end of the webinar. At this point, I would like to turn the presentation over to our experts for today. For our webinar today, we have Dawn Nall, Program Manager at the Southwest Environmental Finance Center. And we also have Nick Willis with us, a Program Manager at the Environmental Finance Center at Wichita State University. Dawn and Nick, welcome and take it away.
Okay. Before we get started into the questions, Don and I both wanted to outline a little bit about some of the goals that you may have in your drinking water utilities energy management program. These goals include improving energy efficiency and managing total consumption, controlling peak demand for energy, managing energy cost volatility, and improving energy reliability. Now, some of those goals may be more appropriate for your utility than other goals. So it's important before embarking on the process of energy management to try and outline what are the driving factors and where your goals should be headed towards. If we can go to the next 2 slides. So when we look at improving efficiency and managing total consumption, the first thing we need to realize is that for most drinking water utilities, the actual financial cost of operating your utilities, so your pumps, your motors and things like that, is going to be put into 2 main components. The first of these is the quantity of electricity used on your energy bill. It'll generally be expressed in kilowatt hours or the abbreviation kWh. And then depending on both the size of your facility, the electrical load at it, and the utility you're purchasing from, the electric utility you're purchasing electricity from, you may also have demand charges. And demand charges are generally expressed in the format of peak kilowatt demand, and Dawn will be going into this a little more later in the presentation. But it's important to note that it's not just the total amount of energy used, it's how much you use at the peak when you have the most motors and pumps on in your facility. It's also very important, and Don will be going into this, that if you're going to design an energy management program, to design it so that you minimize your cost based upon the rate structure that you're in within your utility. So beyond that, we can also look at controlling peak demand for energy. On the next slide, electric utilities will typically include this demand charge in their rate structure. One thing you can do is to lower the variability in electric demand over time. So basically, if over the course of a day your electrical demand is more or less stable, you have a very flat electrical demand. This will minimize demand charges at your facility, and the kind of opposite of that is if you have a lot of demand for some period of time and then very little demand later period of time. That is typically going to be a more expensive way to operate your water distribution network, your water treatment plants, is if you have a lot of spiky on-off electrical demands. So sometimes the actual bigger cost savings when it comes to water treatment facilities is to minimize demand charges, not necessarily reduce the total amount of energy used very much, but reducing those demand charges from your electrical utilities. On the next slide, we'll be talking about managing that energy cost volatility. So we often think of energy cost volatility, the first and foremost is it hits us as consumers in our pocketbook. We see gasoline, diesel prices fluctuate quite rapidly. Also, natural gas historically has been quite volatile. Sometimes this is reflected within your electrical pricing as well. And if there are pretty dramatic changes in energy price over a short period of time, that can be very difficult on being able to stay within your budget. So kind of the best way to protect against volatility of energy is to reduce your need for it. And this is what most of the presentation is geared at. We can also look at long-term procurement of energy. We won't go into a lot of detail of that today because it varies so much on a state-by-state basis. But if you go out to a search engine, look for power purchase agreements, those are becoming more and more common, and depending on your electrical load, you may be able to get into a long-term contract at a fixed price, depending on both the size of your demand and kind of the state regulatory controls over energy purchasing by end users. There's also provisions, what kind of alternative energy sources are available, either through, a power purchase agreement, something like that, or even on-site generation of energy. Finally, on this section, we'll be talking about improving energy reliability. So when you don't have power at your facility, that can be either not that big of a deal or almost a crisis level situation. So depending on the criticality of the facilities in your utility, we might be better focused with energy management to ensure that you have power to those critical facilities. And this basically is improving the reliability of the incoming electrical supply and or allowing for backup generation to keep the critical functioning of things like pump stations and treatment plants. There's also sometimes is that power quality can vary depending on where you are in an electrical distribution network, and poor power quality can sometimes knock out components within treatment facilities or motors or various control systems. So there are also ways to address the power quality at your individual facilities. So with that, I'd like to show on the next slide kind of the breakdown of how water treatment energy use breaks down. Now, water is always a very, very local issue, and this is a slide that is a reasonable generalization of a surface water treatment facility. And this is the total energy demand used at a typical surface water plant. What we see is that the majority of the pumping, and for some reason this arrow moved, the 67%, the largest part of the pie here, is finished water pumping. And then raw water pumping is the 11.1%. So we're close to 80% of the energy use within a surface water treatment plant. In a conventional kind of treatment train will be in the water pumping, both raw and finished water pumping. So anytime we look at managing energy, reducing the usage of it, we kind of look towards the largest energy users first. So this guides us, and we'll be talking mainly about water pumping within this presentation. And with that, we'll now start the questions with Dawn. So I'll turn it over to her.
Thanks, Nick. So we just wanted to note that we did receive some questions that were kind of regional or state-specific questions, asking about things such as extreme temperatures or specific regulations. We felt rather than address this on a national webinar, that it would be wise to address it on a one-on-one basis. So if you submitted some of those questions, or if you come up with some of those questions throughout the course of this webinar, you can email either Nick or I, and our emails will be available at the end of the presentation, the end of the webinar today. Or you can request that one-on-one technical assistance, and the web address is at the bottom of this slide. So you can ask for more assistance with energy management or any of the other topics that Savannah presented earlier. So we just wanted to make you aware of that. And we're going to dive right into our first question. So the next slide. How can I do a quick evaluation of my system? So there are lots of ways that you can do a quick evaluation, but one of the first things you should do when assessing your energy use is to make sure that you understand your energy bills. Next slide, please. So understanding your energy bills is important, and not all energy bills look the same. So this is an example of one bill, and as we look at the bill, it looks like we have very simple charges. And then this next one, sorry, Savannah, go ahead and go to the next one. This next one is much more complex. So understanding your bills, understanding what you're being charged for is really a smart first step. So when we're looking at this type of bill, we want to understand what the bill is for. And this goes for really any type of bill. Which building, what equipment are you being charged for? And if you're not sure, then you need to find out. We've worked with water systems that have been paying the golf course's energy bill for an unknown number of years until they went through the process and identified what all their bills were for, and then they realized that they were paying for the golf course. So it's always wise to make sure you know what you're paying for, and then understand what are the rates that you're being charged. So are you being charged a flat rate? Are you being charged a variable rate? Are you being charged on peak, off peak? Are you being charged seasonal? This bill has it all. If you look, you can see that there's winter charges, there's summer charges, there's on peak, there's off peak. There are other fees for renewable energy riders. There are economy demand charges, so there's demand charges on this bill. So as you look at your bill, it can be simple, it can be complex, but understanding what rate you're being charged is important, and making sure that that rate matches your intended use is the next step. So understand what's on the bill. Are you charged demand charges? Do you have the time of use options? And can you optimize what you're paying for? So you want to make sure that you work with either your energy provider or the EFCN or another technical assistance provider if you don't have the answers to all those questions. And any one of those groups should be able to help you understand those energy bills better. Once you're familiar with those bills, then you can establish your baseline. What that means is you start tracking your energy use over the course of you want to start with the course of a year and really look and see where you're at right now. And as you implement energy savings, you can start to track that. So we'll talk later about some tools that are available for tracking baseline, but understanding your energy bill is the place to start. Next slide, please. When we look at the energy bills, there are some typical components that you'll see. So just to be familiar with your bill, you will see your customer charge. That's kind of a fee that sometimes we charge our water customers as well. That's just to have service. Whether you use any energy or not, you will pay that fee. Not all bills include that, but a lot of them do. Your consumption charge, that's how much electricity you're actually using. That's by kilowatt hour. And then some bills have demand charges, and again, this may not apply to some rate structures, but for a lot of water utilities, you're going to see a demand charge. And demand charges may be the bigger portion of your bill. So understanding what you're being charged and how you create demand is important. And then oftentimes there will be other charges for different types of service or growth or grid or you name it. Just like we have a long list of charges that we could possibly charge for water, so do our energy companies. And you may be able to switch rate structures if it seems like what you're being charged isn't appropriate. Sometimes systems have a change in population, and so they were using more kilowatt hours or they had a higher demand rate, and it's decreased because of population decrease. And the rate structure from the energy company never changed to reflect that decreased use in energy. So that's an example of when you would want to switch rate structures. There are many other times out there whenever a system was built or a pump station was installed and the water utility provided information to the energy company, and then it turned out to not be used the way that they thought it was going to be used, but the rate structure was never changed to reflect the actual use. So you may be paying more than you need to because you're on the wrong rate structure. So you may be able to switch rate structures. Sometimes energy utilities limit how often and how many bills you can change at a time. So again, that's something that you would want to work with your energy provider on. But it is possible to save money by switching rate structures in many occasions. Next slide, please. The next thing that we recommend for a quick evaluation is to understand your system. So you want to make sure that you understand your equipment age, your maintenance history, your operational history. All of those impact decisions about upgrading or replacing equipment. So you want to look for ways to optimize your operations. And we have a link here for a publication that was a tech brief. If you do not know where you're operating at on your pump curve, or you need a refresher on how to read a pump curve, or pump curves look like Greek to you, then I would highly recommend that you take a look at this tech brief. It's very straightforward and explains reading pump curves quite nicely. So if you're not operating on your pump curve the way it was intended or designed to be used, chances are that pump is not being used efficiently as far as its energy consumption. So make sure that you understand your system, your pumps, and how they were intended to be used. And then another big one for consumption of energy is air compressors. So if you have a plant that has valves that are opened or closed with air, and you realize that your air compressors are running even when no air is being used, it's a good indication that you've got leaky air lines and you're wasting a lot of energy. So look for ways within your system to optimize your operations. Next slide, please. And then you want to understand your buildings. You want to make sure that your building is pretty airtight, that you don't have air conditioning or heating leaking out of those windows or doors. Oftentimes in our water plants, we have lots of other penetrations into the building. where pipes enter or exit, or we have exhaust, facilities going out the roof. So we want to make sure that we're not losing any conditioned air, whether it's hot or cold, out of those penetrations. Of course, you want to look at your lighting. Is it efficient? And are you only using it when you need it? I know that a lot of times lights get left on in the bathrooms, and it's just unnecessary cost. And then, are your thermostats working? Are they set at the right level? And this also comes back to looking at space heaters. We like to use space heaters in small water utilities in our pump houses and in different small buildings that don't have heat built in to avoid freezing, which is wise. But oftentimes we turn those on in the fall and we turn them off in the spring. They're not controlled by a thermostat, and then we get a nice, like 65 degree, 70 degree day, and the pump house is a sauna. So we're just wasting a lot of energy whenever we don't use thermostats properly, or we don't bother to turn space heaters off. We also have a tendency to have condensation in the summertime whenever we have cold water running through pipes and we use dehumidifiers. Those are another place that energy can really be wasted. Not that you shouldn't use them, but you should use them wisely. So you want to understand what's causing temperature changes in your buildings. Is equipment heating it up? Is cold water cooling it down? Is the cold water in the pipe causing the condensation? What can you do to control those, and how can you use them wisely? So those are the kind of quick evaluations of your system. And we will go to the next question. Oh, I lied. I apologize. So I wanted to make sure, too, that we understand your distribution system. In this case, the most important concept is water loss. If we are pumping water, if we are producing clean water and putting it out into our distribution system, and then we're losing it, all of the energy that we use to generate that clean water is also being wasted or lost. So really understanding your water loss is an important concept, a quick kind of evaluation that you can do. And you should start understanding water loss by starting with a water audit. And AWWA has that software available, and we'll give you some information about that in a little bit. You also want to understand the pressures in your system. If you're using booster pumps, are they on VFDs, variable frequency drives? Do you maintain your PRVs, your pressure reducing valves, and any other valves that are used to control pressure zones, whether it's gate valves to isolate? Do they seat properly? Do you have any leakage? All of those lead to system inefficiencies, and system inefficiencies lead to wasted energy. And Nick will talk more about system inefficiencies with our next question.
All right, so this question, and we had several questions kind of the same vein, like how can I tell if something is efficient or not? And this question specifically focused on pump stations. The inefficient ones often look the same as the efficient ones. How can we tell the difference? When we first look at pump station efficiency, the question submitter is absolutely correct. Just looking at equipment in and of itself may not be the way to judge whether or not equipment is providing the service in an efficient manner. So the next slide kind of shows us some of the ways we can begin to judge pump station efficiency. First, going back to Dawn's point, understanding your meter readings and the bills that are tied to each pump station is important. If you don't have the actual energy use at the facility of concern, you need to get that prior to beginning to judge the efficiency. So you can kind of do some quick calculations, and a relatively simple calculation would be to total up the total gallons pumped within a month, and hopefully your pump station units all have individual meters that you'd be able to do that. You would also need to have your kilowatt hours for that same month. And then to make things equal to each other, you would need to also include the amount of pressure increase within your calculations. So you do that for one pump station and a second pump station, and you can begin to see, oh, to increase, 1 psi of pressure, and this one takes quite a few fewer kilowatt hours per gallon pumped. So that would be a good way to baseline within your own system which pump station is more or less efficient. There are some things you can also, just by visiting the pump station and looking at the records that have been maintained for that pump station is the pump station actually being maintained? Maintenance is a very good indicator of the efficiency of operational equipment. If you're doing, preventative maintenance per manufacturer schedules, you're much more likely to keep things operating in an efficient manner. Another thing at some pump stations that they often have multiple pumps for redundancy. If you have some of the equipment components that are out of service, or if some of the control systems have been bypassed, that's a good indication that the pump station is not being operated as it was designed to be operated. So if it's being operated outside of the design, that's a reasonable indication that it might not be a very efficient pumping station. And finally, what we can do is kind of look at the distribution system. Is that the distribution system that the pump station is supplying, is it a leaky distribution system? So we do talk about water loss a lot here, because you may be able to pull out a pump and replace it with one that's 3 or 4% more efficient, but if it's going into a distribution system that's losing 35% of the water that's pumped into it, your first method of reducing your energy usage by, say, pump replacement, your time and money might be better utilized by dealing with some of the water loss within your systems. On the next slide, we're going to be talking about some inefficiencies with moving water around itself. So there's some relatively common distribution system inefficiencies out there. The first of which can be described as looping of water. So this is not the elimination of dead-end pipes in our distribution networks by connecting two dead ends and allowing water to flow freely within the system. This is when water is being pumped to a higher pressure zone and then bleeds back through a pressure reducing valve to the initial pressure zone. So basically, in this scenario, you're running a pump, sending water uphill, and then it comes back down through a pressure reducing valve to the initial pressure zone. That is just wasted energy. There are sometimes it's probably justified as a way to maintain water quality in one or both of the pressure zones. But it's a pretty expensive way to maintain that water quality because you're just burning up energy. Another inefficiency within distribution systems is using a more expensive supply. This can happen both in groundwater and surface water supplied water systems. So basically, are you using the cheapest supply possible when you're supplying a pressure zone? This is more common with larger systems or rural water districts that have a lot of variable terrain within them. But one of the main costs for water supplies is the energy cost. So if you're running, say, for example, water from a well that has a water table 500 feet below the surface and are not running water from the well that's 100 feet below the surface of the ground, that would be a good example of you're using the more expensive supply. We also see sometimes that pressure zones are being quote-unquote leaped. So basically, let's imagine a 3 pressure zone system. Water is pumped from the lowest pressure zone to the highest pressure zone, and then the middle pressure zone is supplied with pressure reducing valves from the highest pressure zone. To make this scenario more efficient, you would have water being pumped from the lower to the middle pressure zone. Therefore, you're not over pressurizing the water only to bleed off that pressure with pressure reducing valve later on. Finally, there are some water distribution systems that have too high of pressure. And this often is the result of variable terrain, but too high of pressure leads to more leaks at things like pipe joints, customer service connections. So because there's an energy cost to supplying water, adding pressure zones sometimes can be an energy savers by reducing pressure in the highest pressure zones of your system. With that, hopefully this helps explain the question with inefficient pump stations. But like with so many things with water utilities, your mileage is going to vary. Each system is unique. So understanding the flow of water in your system is probably the first thing to do here. With that, Dawn will continue on with the next question.
What is the easiest change to minimize energy use? So the easiest change is probably to turn off your lights and then to replace your old light bulbs with more efficient light bulbs. But when we're looking at water utilities, we probably want to look at process changes. So if we can go to the next slide. Our process changes can eliminate energy use in running something for fewer hours in the day, or looking at when we're being charged the most. So change the way that we operate or the way that we run our system. It doesn't really cost us anything to make those changes, but it can save us money on our energy bills. So looking at ways that we operate, that we could operate differently, is what we want to find here. So we have an example of demand charges being high, and those demand charges are being caused by the high horsepower pumps for backwashing our filters. So when those pumps come on, they have very high demand charges, but the fact of the matter is we only use those backwash pumps occasionally. We don't run them every day. We don't run them every week in some cases. So when those pumps come on, it drives the demand, but we don't need to use them very often. So if we could look somewhere else in our process where we could turn something else off that would be equal to those high horsepower backwash pumps, and we only needed to turn them off for that little bit of time that we're backwashing every week or month, we could reduce our demand charges. Nothing's really changed except the way that we operate, but our demand charges have dropped and our energy bill has dropped. So looking for those process changes that are causing things to increase on our energy bill are great ways to make fast changes and have quick wins for saving money. If we can go to the next slide, please. So there are several different places that you can look for these types of opportunities. So not just process changes, but other ways that we can capture energy efficiency. Of course, there's always a capital program. And when we say capital program, we're usually talking about some, big dollar amounts. But sometimes not so much, but we can look at equipment replacement. And then we did talk about the process change being one of the easiest ways. Operational changes right there with process changes. Another method is to look at going to automation or controls. And we'll touch on this a little bit more later on this afternoon or this morning, depending on where you're at, and the benefits of automating. And then maintenance improvements, as Nick said, maintenance is a really good indicator of lots of things in your system. If your equipment's not being maintained, especially our pumps, and we're not operating the way that the pump was intended to be run, chances are it's costing us more in energy than it needs to. And then you can look at other business measures that you could change to decrease your energy consumption, and that might be your lighting program. So all of those are just opportunities for you, places that you can look for energy efficiency. Next slide, please. And then when you're looking at picking some projects and thinking about what you can change, what you might be able to do, these are some of the highest impact projects that are out there. So if we're looking at optimizing our water system, we're looking at saving energy. If we're finding inefficiencies with our pumps and we can overcome those inefficiencies, again, we will save money. Looking at your motors, how many motors do you have, and are you managing those motors based on how they use energy? So motor management. Promoting water conservation. If we don't have to produce as much water, we don't consume as much energy. And then of course we want to look at our heating and cooling loads in our buildings and our well pump houses. And then finally, if you have good sources of renewable energy in your part of the country, whether that's solar or wind, some of our wastewater systems are now doing cogeneration, and it can be used at the water plant, depending on your physical location to the wastewater plant. Other types of renewable energy, those will all, of course, reduce your energy bill for electricity. So those are just the potential high-impact projects. So those are the kind of the quick ways, and then other ways that you could consider to minimize your energy use. So I will turn it back over to Nick now.
Okay, and this next question coming up has to do with variable frequency drives and whether or not they can pay for themselves in energy. So the question is, for a small system with 1 or 2 wells with submersible pumps, which is a very common situation for a small system to be set up like, can high efficiency motors and variable frequency drives pay for themselves in energy? So we'll start talking here about electric motors on the next slide. Electric motors drive most all of the processes and pumps within water and wastewater distribution systems. They are kind of an incredible advance. When they first came out, they are extremely reliable. If you take one takeaway from today, this next bullet point, that about 90% of the lifetime cost of an electric motor is the electric bill and not the acquisition of the motor itself. It's very, there can be some pretty strong business cases for when you replace a motor that it should be efficient. Electric motors can also be rewound several times at motor shops, which basically that's kind of like a pump overhaul equivalent for an electric motor. Electric motors are very standardized and are very readily available. There is NEMA, which I can't think of what that stands for. They have different frame sizes, different horsepower ratings, and electric motors for most sizes and applications are kind of a commodity product. It's important to note that electric motor failure may actually be a sign of other problems. The motor itself may have been fine, but you had poor power quality, or it was connected poorly, and that just because an electric motor fails, the actual cause of the problem may not be the electric motor itself. And then for most treatment plants, you're going to see totally enclosed fan-cooled motors. So when you go out there kind of looking at what's on the market, for most kind of processes, it's going to be a TEFC motor. On the next slide, we talk about motor efficiency. General rules of thumb. The larger the horsepower or kilowatt rating of it, they are going to be better at converting the energy into work for the motor, so they're more efficient. 3-phase motors also typically are more efficient than a single-phase motor, but single-phase motors in most applications are going to be relatively low horsepower, maybe 2 horsepower or so at the most. So most of your larger pumps and things like that are going to be 3-phase. And motors then are typically most efficient operating at about 75% of the nameplate rating. So this would be a 75 horsepower load on a 100 horsepower motor. That would kind of get you in the sweet spot for electrical efficiency. So on the question of whether the motor replacement will pay for itself on the next slide, the answer is it really depends. What does your energy cost? How many hours a day does this motor run? What is the cost of a new motor and the installation? And then what's the relative difference in efficiency between the motors? The economic case is going to be improved as you have more expensive energy costs, longer run times, and greater differences in efficiency between the two motors. So on a case-by-case, you'll kind of have to do the math, taking these things into account. However, for future motor purchases on the next slide, we give you some ideas as to what to do. A lot of people in energy efficiency are advocating for some sort of policy on motor replacement. All replacements should be NEMA premium rated, so that's kind of the highest efficiency on the market. Multiple manufacturers make these in most sizes. There's also a super premium efficient motors that are coming out in the future, and some motor manufacturers also already claiming. An important thing about these is that they are controlled with they're kind of a different type of winding, and they can go much slower with variable frequency drives than existing most common motors on the market today, and that there is some applications where gearboxes can be removed, and that is a huge leap forward in efficiency. This is mostly being done on cooling towers, but I would suspect it starts to be into the water and wastewater market in the coming years. One thing you might want to consider is that motors that are in service a lot of hours a day, that you replace them with the NEMA Premium and don't rewind them. However, the motor rewind shops are getting in on the game of guaranteeing efficiency and showing you test results on the rewind. So, you know, in the spirit of recycling and utilizing existing resources, we can take it to a motor shop that can guarantee us basically a NEMA Premium motor efficiency on a rewind. So do your homework when you're looking at rewinding your motors. On the subject of variable frequency drives, on the next slide, there's a kind of table on the right side. Basically, variable frequency drives change the frequency of the incoming electricity, slowing the motor down. For centrifugal loads, which is most water pumps are centrifugal loads, and most aeration blowers are also centrifugal loads, there's something called the affinity law, which the horsepower required is related to a cube of the speed. So if you can slow it down, you can have linear proportional drops in flow and much higher than linear proportional drops in horsepower. So going from 100% speed to 80% speed will get you about 80% flow on a centrifugal load, but will only be 51% of the horsepower required. So this is why if you've ever questioned you know, what the salesmen are telling me about such high energy efficiency savings from variable frequency drives, this is what is going on. It is important to note that it requires inverter rated motors in order for variable frequency drives to operate. Most newer motors are inverter rated, so there's definitely savings opportunities here. When we're looking at it, the next slide kind of gives you some other benefits of variable frequency drives. So first of all, the power savings as shown by that chart, they can be pretty strong. They also are basically a soft start and soft stop capable. So basically, you slowly turn on your equipment and you eliminate the sudden input of power that across the line voltage does. So this reduces equipment wear and tear, so your pumps will last a little bit longer. And you can also reduce pressure spikes within your distribution system. There are some case studies of distribution systems that go from something like 20 main breaks a year, they install VFDs and they're down to 1 without any other changes. So if you know you have pressure spikes within your distribution system, installing variable frequency drives can be a huge win for you. They can also improve power factor. So if you have KVA on your bills and are being charged for it, variable frequency drives might help you out there. And then they're readily programmable with programmable logic controllers and SCADA systems. So when should we add them? The next slide kind of gives you some things to consider. First and foremost, it's generally going to be cost effective if you have a pumping station where you have a throttling valve that's partially closed immediately after the pumping unit. Basically, your variable frequency drive can generally allow you to remove that valve or fully open it and slow down the amount of water entering your distribution system that way. It's important to note you may just have too big of pumps. There's a lot of overbuilt systems out there, so you might want to check to make sure your pumps themselves aren't too big. And then it may also be cost effective in various high main break situations, if you have pumps that run quite a few hours a day, if you're otherwise looking to automate or upgrade your control systems, if you have very high cost electricity, the savings can come pretty fast. And then also variable frequency drives are very useful if you have to remove your elevated storage for maintenance. Your variable frequency drive and the control system can basically keep a consistent operating pressure in most distribution systems without the need for an elevated tower. So you can run for a couple weeks while the tower undergoes maintenance and repairs. And with that, we'll turn it back over to Dawn. For the next slide.
Hey, Dawn, are you there?
Yes.
Perfect.
Oh, back up one more. There you go. So we had a question about water loss, and water loss, as we've mentioned, is directly tied to energy consumption. So I think that we've both mentioned now that if your distribution system is leaking, you are wasting energy every time that a pump runs and pushes water out there. So the question came in, is there data available across multiple utilities for water loss? And indeed there is. AWWA has a water audit compiler, and it's a way to look at water audit data from multiple water utilities. So the website to obtain that data is listed there. And if you have questions about how to use that, we'd be happy to help you. I'm sure the AWWA would as well. So there is information out there to look at water loss across multiple utilities. And so that was a short and sweet one. I'm going to turn it right back over to Nick.
Okay, we also got several questions similar to this one. What are some ways to modify or replace existing equipment, operations, and infrastructure to gain long-term energy cost reductions? Again, a lot of this goes back to understanding your existing system. So the next slide, we're going to start with the existing equipment. First, one thing that a lot of systems are starting to do is utilize predictive maintenance, which is basically using things like ultrasound, thermographic cameras, and thermographic cameras are really cheap now. For a couple $100 bucks, you can get one for a smartphone. And they can identify problems that are going to, failures that are going to occur in the near future if you don't rectify the problem. So a lot of utilities and maintenance personnel are getting into that game. Proper lubrication can also save maybe up to 5% on gearboxes. There's energy efficient lubricants out there on the market. You probably need to have a pretty good supplier who will work with you and provide you with some appropriate. If you have belt-driven equipment, a cogged belt, replacing a V-belt can save you about 2% in energy savings. So it's not world-changing, but if you do that across a lot of equipment, that will save, a few $100s to low thousands per year, depending on what you have. Keeping lighting clean can also help with the existing equipment. On the next slide, we talked about existing operations. Can you change your existing shifts to take advantage of some of the cheaper energy which may be available in your billing system? Can you automate pumps? Obviously, tracking energy usage is very important. It's hard to optimize something if you don't keep track of it. And that may require some additional meters within your plants or your well fields. There's clamp-on amp meters for 3-phase that are relatively affordable, and you can, tell individual pieces of equipment which may be operating more efficiently than others that way. Also, we haven't talked much about it, but vehicles use a lot of energy. What can we do there? A remote meter reading can really reduce the vehicle mileage, and also control systems. If you're having to drive out several miles to turn something on or off several times a day, definitely consider automating that. The next slide we talk about is this. Minimizing the number of times water is pumped. Sometimes water is pumped several times when a single pump could do the same work today. This is often the result of legacy infrastructure. So you lose efficiency the more times you pump water. Having a water model and knowing where high velocities exist within distribution system can also be pretty effective. That can say, hey, this is the area of pipe where we have the most friction losses, meaning we're using energy and it's just being dissipated within friction between the water and the pipe walls. We would strongly recommend doing a water audit to track your water loss from year to year. If you have high water loss, that may be the first target to reduce your energy usage. Also consider reducing your regular flushing through distribution system upgrades. This might be looping, where you have dead ends, to eliminate those dead ends. It might also be putting chlorination out there in the distribution system to maintain chlorine residuals. And it also might be changing your treatment plant or possibly some of your storage operations to reduce disinfectant byproduct formation. With that, we'll turn it back to Dawn.
The next slide, please.
Yep.
So here's a quick listing of some of the tools that are available to help. So we talked early on about establishing your electricity baseline. The EFCN has developed a Microsoft Excel-based spreadsheet tool. So you can enter in as many energy bills as you want per version or per file, and you can start tracking how much energy you're using. It produces some nice graphs for you and helps you to track that energy use. Also, EPA's Energy Star Portfolio Manager is a bit more complex with a bit more outputs than the baseline builder, but it starts by establishing your baseline. And if you're on the wastewater side of things, Portfolio Manager kind of lets you compare your efficiency with other systems similar to you. A great place to start if you're not sure if you have potential for energy savings is NYSERDA's water checklist. It's just 10 questions. You check the boxes, and depending on your score, it says you have potential to save energy or not. And I don't think I've met a system yet that hasn't had the potential to save energy. So, but the questions really get you thinking about your system and where you're consuming energy and where you might be able to make changes. And then the energy.gov has a software tools list. So if you're looking for pump motor management, or you're looking for blower motor management, or other types of energy consumers, there are tools out there that can help you track and manage those motors. So energy.gov is a great source. And AWWA released a manual for energy management for water utilities just last year. So it's very current. I want to make sure you're aware of that document. So those are some tools that are out there right now. And if you have questions about other types of things that are available, don't hesitate to ask. All right. So again, another short and sweet one for me. Nick, back to you.
Okay. The final question we're covering today is, how can we plan for future energy challenges, both availability and cost? This is a very large question, and we'll try to answer it relatively quickly. First, really, we can't stress enough, know your energy bills, track your usage, try and uncover the inefficient places in your system, and know what those demand charges are. I think a lot of systems are surprised when they realize the percentage of their total energy costs that goes to demand charges that may be able to be offset. You'll get a thumbs up from your boss and your board if you're able to eliminate a few $100s a month through some process changes we detailed earlier. Know where your system's inefficiencies are, and over time, try and plan to remove them. And then, set some sort of internal policy that you evaluate the efficiency of equipment when you purchase it, and purchase only efficient equipment. It may not always be purchasing the most efficient piece of equipment out there on the market, but definitely bringing that into your total life cycle costing. The next slide, asset management, maintenance of your system and equipment. That's very critical to controlling energy costs, because well-maintained equipment is efficient equipment. Incorporating energy efficiency into capital improvement planning process. So do you have that hydraulic model? Are you utilizing it to eliminate the fast flow, high head loss areas of your system? Are other energy efficiency items being taken into account? Then pay attention to new energy opportunities. The electric utility market is changing very, very quickly, probably faster than it ever has since it first was built out. Electric utilities may be offering things in the future for you, such as efficiency audits or rebates, or even different pricing schemes in the future that you may be able to benefit from. Finally, on the next slide, going back to the idea of water loss. The AWWA water audit software spreadsheet tool is a very good, effective tool to utilize if you have high water loss within your system, to track it, to try and identify where that water loss is occurring. By utilizing this, you can begin to implement some of the solutions. It will help you maintain good records of things such as energy costs, and performing annual audits for water loss within your system is a good way to keep a lid and a good structure around the energy management within your system. With that, I'll turn it back over to Savannah.
Thank you, Nick. So quickly before we wrap up, I just have 2 final polling questions for our attendees. And the first one is if you would like to subscribe to the Environmental Finance Center blog. If you want to sign up for the blog but do not have the opportunity to submit your polling answer today, you can sign up for the blog on the EFCnetwork.org website. And getting ready to close that poll in 3, 2, 1. And lastly, if you are a small water system of 10,000 or fewer people served, are you interested in receiving in-depth technical assistance? If you're unsure about technical assistance or do not have the opportunity to submit your answer today, please review the technical assistance form on our EFCnetwork.org website. And again, all of these links to the technical assistance, CEU accreditation email will be sent in the follow-up email. And getting ready to close that poll in 3, 2, 1. At this time, I would like to thank Nick and Dawn for providing their expertise on energy management in the water supply and distribution systems. And thanks to all the attendees who joined us today. Dawn or Nick, do you have any additional closing comments?
I don't believe I do. Thanks for attending, and feel free to contact either of us with any further questions you may have or technical assistance that we may be able to offer.
I'd just like to throw out one quick thought. VFDs can really save utilities money, but oftentimes whenever a utility purchases a VFD, they set them at one operating point and they're using them not as a VFD. So we want to make sure that when we talk about the money that VFDs can save you, that you understand when and where they should be used. So if you have questions about that, please let us know and we'd be happy to talk with you more about it. And thank you so much for your time today and for attending our webinar.
All right. Have a great day, everyone. Thank you.